All right, so 3.9. 3.9, what we're going to do is we're going to talk about how to take the derivative of inverse trig functions, and what we're going to use is we're going to use the derivative of an inverse to be able to pull that off. So what I'm going to do is kind of go through a little bit of pre-calculus with you, just as a reminder of how this is done, because this is what I'm going to ask you guys to find the derivative of the tangent inverse, and I need to see the work for that, okay? So I'm going to make you use the derivative of the inverse to prove it. So this is going to be inverse trig functions, and then their derivatives. So what I want to do is I want to start out with our inverse trig functions. So the value. So what I know is, as long as we're on the correct restriction for like sine and cosine inverse, so we're just going to kind of stick it to quadrant 1 for right now. I know that the sine of pi over 6 is equal to 1/2. So that means the sine inverse of 1/2 is going to be equal to pi over 6. We know when we go from function to inverse, we just switch input and output. Now the sine has a restriction from pi over 2 to negative pi over 2. Remember, you'd have to count backwards on these, but that's how we'd be able to find it. So I know the sine of pi over 6 is equal to 1/2, so the sine inverse of 1/2 is equal to pi over 6. We're basically going backwards. So we know that basically that's with all our trig functions. What I want to kind of get into is what about our mixed compositions. So if I ask us determine the value of the cosine of the sine inverse of 1/2. So it's really nice if we have some easy values here. So I'm going to kind of show you what the value of this thing is, and then I'm going to have to kind of go through the longhand way of how to pull this off, though, okay? Because not always are we going to be given just these pretty values here, okay? So what I know is that this is going to be equal to the cosine. Well, the sine inverse of 1/2 is pi over 6. And then when we go to cosine of pi over 6, it's going to be equal to root 3 over 2. So this is going to be equal to root 3 over 2. Okay, so another way. So if I want to find the cosine, this is actually a more powerful way because it's going to, instead of being crutched by our unit circle, we'll be able to find this for all values, no matter what number it is. So if I want the sine inverse of 1/2. So what we do is we call this expression right here, we call this y is equal to the sine inverse of 1/2. And what we know is when we go from inverse back to regular function, we're going to switch input and output. So I know I kind of jumped the gun here. What I want this to say is I want this to say the cosine of the cosine inverse of a number. That's what I want. I want this to say the cosine of the cosine inverse of something. Because if that's the case, these two functions are inverses, so it's just going to spit out whatever is there. But I can't turn a sine inverse directly into a cosine inverse. What I have to first do is I have to take the sine inverse, so I call this expression here the sine inverse. And if I know that that's a sine inverse, what I can do is I can switch input and output by changing this from sine inverse to sine. So if you go from inverse to function, your input and output switch. Now what's nice is now that I have a regular trig function and non-inverse, I can turn a sine function into a cosine function. I know that through the Pythagorean theorem. So, our Pythagorean theorem says that sine squared of y plus cosine squared of y is equal to 1. So that means this sine of y is going to go here. So this is going to be 1/2 squared plus cosine squared of y is equal to 1. So 1/4 plus cosine squared of y is equal to 1. And when you subtract it, you're going to have the cosine squared of y, which is equal to 3/4. So that means the cosine of y, which is kind of nice that this really right here is your answer, because I called this expression y. So this is actually the cosine of y, is going to be equal to the square root of this thing. Now, you want to know if it's plus or minus. Well, the cosine is only defined up here. The cosine inverse is only defined up here. So when you, so that means it's going to be positive. So this is going to be equal to √3/2. I should be careful. I lied there. The reason why this is positive is because we know that the sine inverse, the only way to go back and forth is if you're over here on the right side of the circle, and the cosine values are always positive over there. All your cosine values are positive on the right half, so that's why this is positive √3/2. Now another way to kind of verify that this is kind of the thing I had here, so I know that the cosine inverse of √3/2 would be equal to y. So I've turned this into this piece right here. Now becomes, I've got to drop it down. So this actually is the cosine of the cosine inverse of √3/2. And now those things cancel, so this is √3/2. Now, once you get the cosine of y, that's going to be your answer, which is the same thing here. You can see that that's your answer. So this extra step isn't technically necessary, but that's really what's going on here. Okay, so that's pre-calculus. I say we do it again. B, what if I ask us to find the tangent of the sine inverse of 2/3? Now I'm picking a number that's not pretty on this unit circle because it forces us to do the method that I did. So what I'm first going to do is we're going to call this thing y, okay? What I want to do is I want to turn this into a tangent inverse, okay? That's my goal, is to make this a tangent inverse. So what I know is that expression right here, we're going to call this y is equal to the sine inverse of 2/3. Now I can't turn a sine inverse into a tangent inverse, but I can turn a sine into a tangent. Because if I have one trig function, I know I have all trig functions. So this is going to be 2/3 is equal to the sine of y. And now I know the sine of y, I know the cosine of y, I know the tangent of y. So I know the sine squared of y plus cosine squared of y is equal to 1 because of the Pythagorean theorem. And this is going to go here. So 2/3 squared plus cosine squared of y is equal to 1. And then when I'm done simplifying this, I'm going to know what the cosine value is. So 4/9 plus cosine squared of y is equal to 1. So that means the cosine squared of y is going to be, no, this is 9/9, so this is going to be 5/9. So when we're done, I'm going to have √5 over 3. And again, remember, this is only defined on the right half of the circle, so cosine's positive over there. So that means the cosine of y is going to be equal to √5 over 3. Now what's nice is I know the sine of y and I know the cosine of y, therefore I know the tangent of y. And as soon as you have this expression, the tangent of y, this is your answer. So the tangent of y is going to be the sine over the cosine. So 2/3 all over √5 over 3. So this is 2 over √5. So this is our answer here. So there's our answer. We have the tangent of y. Okay. What if I say this? What about the sine of the cosine inverse of x? What if I do it instead of having a number? What if I have a variable there instead? Well, nothing changes. You know, this we're still going to call y, so y is equal to the cosine inverse of x. And then we're going to turn a cosine inverse into a cosine, so I'm going to switch the input and output when I take it from inverse to function. And now I know the cosine of y, I can turn this into the sine of y. So sine squared of y plus cosine squared of y is equal to 1. So cosine is x squared, so this is, well, cosine is x, so this will become x squared. Sine squared of y plus x squared is equal to 1. So the sine squared of y is going to be equal to 1 minus x squared. So the sine of y, which is our answer, is going to be the square root of this thing. So this is equal to the square root of 1 minus x squared. so that's our method here. So what I want to do now is, now we've had a little bit of practice in that, we're going to find the derivative of the tangent inverse function, and we'll find the derivative of a couple of these. I'll pick a couple. So finding the derivative of the tangent inverse. So if I have y is equal to the tangent inverse of x, I want to find its derivative. So what I know is I know the derivative with respect to x of f inverse, or f inverse prime of x. So the derivative of this thing is going to be 1 over f prime of f inverse of x. So the derivative of this thing is going to be 1 over this. So I need to know what f is. Well, this technically I'm saying is f inverse of x, right? So that means the inverse of the inverse is the function. So what we know is that that f of x is going to be equal to the tangent of x. So that means f inverse of x is going to be equal to the tangent inverse of x. So remember, what I need in order to find the derivative, I need to know what the inverse is, and I need to know what the derivative of this is. Well, f prime of x is going to be equal to the secant squared of x. So therefore, using this formula, the derivative of the inverse is going to be 1 over this function evaluated at this function. So what's going to happen is this is going to go into that x location. So 1 over the secant squared of the tangent inverse of x. Now I have to simplify that expression using the method that I was, explaining just a little bit ago. So what I know is that this is equal to 1 over, this is the secant of x, secant of the tangent inverse of x, quantity squared. That's what I mean by secant squared. So I'm going to find this. So first, what is the secant of the tangent inverse of x? So I'm going to ask you guys to do this on a test. Well, what I know is I'm going to call this thing y. Y is equal to the tangent inverse of x. Taking tangent and turning it into, taking the inverse tangent and turning it into a tangent is going to switch the input and output. Now my job is to take a tangent and turn it into a secant. Now I know that sine squared of y plus cosine squared of y is equal to 1. But what I need is I need a tangent. So what I'm going to do is I'm going to divide the entire expression by cosine squared, which would do this. So that's why we have the other expression that says tangent squared of y plus 1 is equal to secant squared of y. So that's just the Pythagorean theorem, part 2. So the first one, and then there's actually 3 of them. The third one is where you divide everything by sine squared. Okay, so this is going to go here. So this is tangent squared, so tangent, so I'm going to square both sides. So this is going to be x squared plus 1 is equal to the secant squared of y. So when I square root this, I'm going to have the secant. So that means this is going to be the square root of x squared plus 1 is equal to the secant of y, which is my expression. That's what I was looking for. So this is equal to the square root of x squared plus 1, which is going to go right here. So now, squish it in the bottom. So now I know that f inverse prime of x is equal to 1 all over the secant of the tangent inverse of x squared. So this is 1 over this expression squared, square root of x squared plus 1 squared. So this is 1 over x squared plus 1. And a lot of times they write it 1 over 1 plus x squared, and I don't know why they care about the order so much, but you'll see that expression more often than that. All right, let's do it again. Oh, well, now we have a rule. Now we have a rule. Actually, maybe we'll list the rules in a second. What if I want to do another one? Let's see, what one do I care about? All right, yeah, you know that the two main ones are tangent inverse and sine inverse. So let's find the derivative of that. Okay. So what we know is, if I want to find the derivative of this, I know that our f of x would be equal to the sine of x. So then our derivative of inverse would be equal to the sine inverse. So what's nice is I can find the derivative of this by using the derivative of this. So I know that that f inverse prime of x is equal to 1 all over f prime of f inverse of x. So what I need is I need the derivative. Well, we know that f prime of x is going to be equal to the cosine of x. And that means this function is going to go right there, and it's going to be in our denominator. So this is going to be 1 over the cosine of the sine inverse of x. Which we've actually already, I think we did. Oh, we'll do it again. So, what is the cosine of the sine inverse of x? Well, we are going to call this thing y again, so this is going to be y is equal to the sine inverse of x. And then when I take it from inverse to function, we're going to switch input and output. And then sine squared of y plus cosine squared of y is equal to 1, where the sine is x. So this would be x squared plus cosine squared of y is equal to 1. And solving this for cosine, we'll finish this. So the cosine squared of y is going to be equal to 1 minus x squared. So that means the cosine of y is going to be equal to the square root of that expression. So that is going to go on the bottom. So therefore our f inverse prime of x, which is going to be the derivative with respect to x of the sine inverse function, is going to be 1 all over the square root of 1 minus x squared. So I don't know what I'm going to ask you guys to do. Either it's going to be the sine inverse or the tangent inverse. Most of the time it's been the tangent inverse. So this method can be used to find the derivatives of all these inverse trig functions. So our theorem is this. Actually, I'm just going to project this. This is our theorem. Is that the derivative with respect to x of the sine inverse of u is 1 over 1 minus u squared du dx. So we found this one. Now if u is a function of x, so u is a function of x. So that's just the chain rule again. We found this one too. 1 over 1 plus u squared times du dx. And all these other ones can be found just using the exact same methods. The only ones I'm going to force you guys to do by hand is either the sine inverse or the tangent inverse. You're going to have to do one of the. Actually, it'll be one of these three. How about that? Okay. I need you to know how to do at least one of these three. But for the most part, I want you to memorize them because I'm going to be asking for these derivatives. The only time I'm going to make you do it by hand, I'm going to ask you to prove it. Okay. It'll say prove it using the derivative of the inverse. If I don't say prove it using the derivative of the inverse, just memorizing these will be enough. To be honest, what I'm going to make you guys memorize is the only ones I care about are these three, okay? You might be asked to find these other ones in the homework, but on a test, those are the only three I care about, okay? So, find the derivative using the rules. So using the theorem or the rule basically says it just, you can, as long as you have these things memorized, you can just look them up and then find them. So what I'm saying by that is these are the derivatives. If you remember them, then just use them, okay? So what I'm going to ask us to do is, what about the y is equal to the sine inverse of 1 minus t? So your entire chapter just asks you to use these rules to find the derivative. I don't know if there's a prove one in your homework, but I'm going to tell you on the test, I'm going to ask you to prove one of those three. But, oh, that's only one question. Everything else is just use these rules in order to do it. So what I know is that this is going to be the sine inverse. So y is equal to, what we know is when we look at the sine inverse, it's 1 over 1 minus u squared times du dx. So this is my u function right here. So this right here is your u. So what I know is, using this rule, it's going to be 1 over the square root of 1 minus that u squared, so 1 minus t squared, that's your u squared, multiplied by the derivative of u, so the derivative of this is negative 1. And I think I can clean up the bottom a little bit. So we know that this is going to be equal to minus that negative 1. This is 1 over the square root of 1 minus, when I FOIL that, I'm going to get 1 minus 2t plus t squared. So what's going to happen here is this negative is going to distribute through, so it's going to cancel this 1, and these two sides are going to swap. So minus 1 all over the square root of 2t minus t squared. B. Y is equal to the tangent inverse of the natural log of x. Again, this piece is your u. It's the tangent inverse of u. And if we go back to the rules, what we can see is the tangent inverse of u is 1 over 1 plus u squared times the derivative of that u function. So this is going to be the u. So y prime is going to be equal to 1 over 1 plus this thing squared. 1 over 1 plus u squared, times the derivative of this. Now we know the derivative of this is 1 over x. So I guess the best we can do is just put that x on the bottom. And we're done. Yep, that's it. I can do one more. C. Y is equal to the cotangent inverse of the square root of t minus 1. All right, so going back to the cotangent, what we know is the cotangent looks like this. It's negative 1 over 1 plus u squared, so it looks a lot like the tangent inverse is just negative. Same thing, the sine and cosine, they're just negative. So what I know is that y prime is going to be equal to 1 over 1, well, negative 1 over 1 plus u squared times du dx. So remember that this thing is your u right here. This is your u. So this is going to be minus 1 over 1 plus, well, u squared is going to be this root t minus 1 squared times the derivative of that. Now, remember this thing is t minus 1 to the 1/2 power, so its derivative is going to be 1/2 t minus 1 to the minus 1/2. Now when we clean this up a little bit, minus 1 over, this is going to be 1 plus t minus 1. The root and the square are going to cancel each other out. And I still have 1 over 2 root t minus 1. What we'll see is those 1's will cancel. So this is going to be minus 1 all over. So there's just going to be a t left on the bottom. So this will be 2t root t minus 1. So this t is going to go. Not a very big section when it comes to finding the derivatives. Really, the idea is these are the derivatives that we care about. Can we remember these right here? And can we use them if I give you the formula?